In the last video, we looked at the beating phenomena. So, what happens when two close frequencies interface with each other and create that characteristic rise and fall in amplitude, right? So, today we go one step further. So, what happens when your machine's operating frequency doesn't just get close to its natural frequency, but it matches it exactly? So, of course, the answer for this question is the resonance, and the results can be very dangerous. So by the end of this video you will be understanding the exactly what resonance is and why it happens and how to spot it on a vibration spectrum, and most importantly in the last we will be covering up that what engineers do to prevent it. So let's dive into it. So before we dive in, let me quickly connect this to what we covered last time. So last time we have discussed beating phenomena. So what is that beating phenomena? That's when two vibration frequencies are very close to each other, they interfere, they add or they subtract, and we will get the rhythmatic envelope and amplitude going up and coming down and going up again. So now in beating the two frequencies are close, but they are still two separate frequencies, right? So the machine's operating frequency is near its natural frequency but not quite at it. So that's why, but in resonance what happens, that resonance happens when the operating frequency equals to the natural frequency. It's not like any close, it's exactly equal. So that one word equal actually makes the entire difference, or you can say that it differentiate between the natural frequency or the phenomena known as the beating. So now to understand the resonance, we first need to understand the natural frequency. So let me explain with the simple version. So every physical object, every structure, every machine or every component has a frequency at which it's naturally want to vibrate. So either you push it, hit it, disturb it, and it will vibrate on that particular specific frequency. So that is known as the natural frequency. Now let's take a very simple example to understand this. Think about a playground swing or a normal swing in a park, right? So if you push it at the right moment, what happened, that at the right frequency the swings goes higher and higher with each of the push. Okay, so in that case we are not pushing it hard, or you can say that we are not working hard to help this swing to gain a momentum. So we are just pushing at the right time. So that timing, or you can say that frequency, is the swing's natural frequency. So now if we'll correlate the same concept into our plant or the manufacturing facilities. So let's say a pump casing, it's having its own natural frequency, a rotating shaft has its own natural frequency, any motor base frame, you can say it's having a natural frequency, pipe structures, or you can say the fan blades, gearbox housing, or you can say each and every component of the machine, all of them, it's having its own natural frequency. So everything that has mass and stiffness has a natural frequency, right? So the formula is very simple and very straightforward, that natural frequency depends on two things. What are those two things? One is the stiffness and second is the mass. So if I will increase the stiffness, or you can say the more stiffness, that means the higher natural frequency. Or if you I will discuss for the mass. So if I will add up more mass, so then it will lower the natural frequency, right? So now you will be seeing this formula, but you no need to calculate anything right now. So what matters in and is that the understanding then that this number exists for each and every component in your machine, and when you force that component to vibrate at exactly that number, so what happens, that at that time the resonance occurs, right? So what actually happens when your machine hits to resonance? Okay, so here is the key principle. So when the forcing frequency, or you can say that your operating speed matches the natural frequency of the structure, so then what will happen, that the energy starts to build up in the system. Okay, or you can say the build up in the machine. So with each vibration cycle, a small amount of energy is adding, right? So and instead of that energy is disappearing or dissipating anywhere, the system absorbing it, what happens, that instead of that it accumulates. So now what will happen in that case, the amplitude will grows with each and every single cycle, right? So in the theoretical system, let's say the machine is operating, machine is there and there is no damping at all in the system. So this is a theory, right? In practical this is not possible because there is always some kind of a damping, right? So let's assume as a theoretical system that there is no damping at all. So in that case what will happen, the amplitude will grow without any limits, and in practice, in real machines there is always some kind of a damping. So that's why what happened, that why there is always some kind of a damping, because the materials is having some kind of a flexibility, bearings are there to absorb a little and the foundations also having a slight flexibility. So but even with the damping, the amplitude at resonance is dramatically higher, okay, so than in any other natural operate, or natural, not natural, but at the operating frequency. So we are now talking about the amplitude multiplications to 5 times, 10 times, sometime 20 times. So the thing to explain here is this, that since the every system is having some kind of a damping, so it's always not that each and every cycle, it's not that always the amplitude going to add up, right? It will compensated by the damping or the flexibility that material have. The material can be bearings, its balls, its shaft, its fans, or the foundations, right? So now that's why what happened, that the resonance always destroy the machine. Even your components is having some kind of flexibility, then also it's dangerous, because still it can grows up to 5 times, 10 times, or you can say the 20 times, depends, right? So now since the bearings are overloaded far beyond their design rating, so what happens, that the shaft is also experiencing some kind of a stress cycles that can cause a fatigue cracking, right? Or there can be a foundation crack, or there can be a bolt loosening and casing fractures, right? So the machines isn't being overloaded by the process here, right? It doesn't mean that it's carrying too much of weight, or running too fast. It's simply or vibrating at the wrong frequency, okay? And here is what makes resonance so dangerous for from a maintenance perspective. So it can appear suddenly, a machine runs perfectly for years, and then something changes, a different speed settings, or maybe some component is weird. Let's say shaft is slightly weird, or fan is slightly weird, or you can say the bearing is slightly weird. So what happens, that shifts the natural frequency and a modification to the supporting structure, right? And suddenly the machine is in comes in the resonance, and the vibration level spikes up, and damage may happen fast, right? So now let's talk about how you actually identify the resonance in practice, okay? Because understanding the theory is one thing, right? And so knowing what to look on a spectrum is what gets you the diagnosis, right? So now the thing is this, first of all we'll be discussing that what you will be seeing in the spectrum. So when you take a vibration reading and look at the FFT, or you can say the spectrum, so resonance has some kind of a its own characteristic signatures, okay? So the first thing that you will be seeing in the resonance is that you will be seeing a broad or some kind of a elevated peak, or you can say the bottom of the peak is slightly broader, right? So unlike a sharp harmonic spike like you are getting in unbalance, or we are getting in misalignment, so resonance tends to show up a wider, or you can say the broader elevation in the spectrum, centered around the natural frequency, right? So the peak spreads across a range of frequency, not just one sharp line. Let's say the resonance frequency is 60 hertz, so you will be getting the peak will be broader at the bottom. So somewhere you can say from 55 to maybe 65, okay? So the natural frequency is 60, but the peak is broader at the bottom, right? So the second thing, this is the first thing that you will be seeing in the spectrum. What second thing that you will be seeing is the overall vibration level will be high, right? So whenever you are in the resonance, the overall vibration level will be high, not because of that there is some kind of a specific fault in the machine, but because the entire structure is being excited at its sensitive frequency, or you can say its natural frequency, right? And what is the third thing? Third thing is the phase behavior. So it's a you can say a more advanced indicator, but it's you can say it's very important to know about this also. At resonance, what happened, the phase of the vibration shifts by 90 degree relative to the whatever the forcing frequency is, right? So if the system is below resonance, what will happen, the phase will be lag, or you can say it's close to zero, okay? And once the machine passes the resonance, or you can say the above the resonance frequency, its approach is exactly opposite, that is 180-degree shift, right? And right at the resonance, what will be the phase? It will be a 90-degree phase. So if you are doing any kind of a test, let's say cost up cost down, or you can say run up run down also, the same test is there. So measuring the vibration as the machine goes slows down, or you can say the machine is slowly picking up the pace or picking up the speed. You can watch the phase shift in the real time as you pass through the natural frequency. So slightly we will now discuss about this cost up cost down and run up run down test. So this is the most reliable way to confirm the resonance. So you bring the machine up to speed slowly. Let's say the speed is 1500, so slowly we'll be running from 300, 400, 500 something like this, and or otherwise we will be costed down, or you can say that we will be run down, right? So what is this run down? Let's say once the speed we have achieved the maximum speed of 1500, then we'll be slowly bring it down. So once the first process is to slowly take it to the maximum speed, and then slowly bring it to the minimum speed. So if there is any kind of a resonance frequency in that range, you will be seeing the vibration amplitude suddenly spike sharply as you pass through it, and then suddenly it drop back and move away. That's it. So that spike, that peak in the Bode plot is your natural frequency. Bode plot we'll be discussing in some another video. What is the Bode plot? Actually Bode plot is nothing but cost up and cost down, the test that we are doing. We'll discuss it later, right? So that spike, that the peak in the Bode plot, it's your natural frequency. This is where your machine is resonating. So once you know that where the natural frequency is, what you can do now, you can check whether your operating speed is too close to it. So what's a general rule that we use in the industrial standards? It's not a standard, but it's a general rule that we want to at least, we need at least 20% separation between our operating frequency and the nearest natural frequency, right? So depends, some machines maybe require more, or some machine may are acceptable with the less also, but at the general 20% separation should be there. So since now we have confirmed that how to identify the resonance, now what? Now there are three main approaches that one maintenance engineer should do, right? And the right one depends on your specific machine and the situation, so you can select based on that. So we'll be discussing three methods. So first method is this: how we can control the resonance is the change the operating speed. So the simplest fix is, if it's possible, if your machine is running at the speed that coincide with the natural frequency, and what the best thing is that try to move the operating speed away from it. Let's say the natural frequency is 1400 and you are using the VFD, just move it to the 1500, or just bring it down to 1200 if your process allows you, right? So that's why some systems are having the VFD that will automatically help you to immediately jump this resonance frequency quickly, rather than sitting at that particular speed during ramp up, right? So the machine passes through this dangerous frequency but doesn't stay there, right? So that's why if you want, you can take the help of the VFDs, and you can pass this frequency, and you can eliminate this resonance, right? Now this is the easiest way. Now what's the second method? But this first method, it's not always we can use it, because sometimes in the process demands that we need to operate this machine at that particular frequency only. So in that case, there are other two methods. What are that other two methods? Now we'll be discussing the second method, that is, if we can change the natural frequency of that particular machine. So if we can't change the operating speed, we can change the machine natural frequency instead. So you remember the formula that we have discussed before. So natural frequency directly depends on the stiffness and the mass. So if we increase the stiffness, what is the increase the stiffness? That adding the bracing, stiffen the base frame, or we can add some support to the to the structure, the base. So what will happen in this case? We are increasing the stiffness, so the natural frequency will rise, right? It will move it away from the operating speed. And what are the other what is the alternative method? That if we want, we can add the mass also. So if we add with the more mass, what will happen? It will lower the natural frequency, right? So sometimes simply just adding a mass block to the base is enough to shift the natural frequency out of the danger zone, right? Now there is also a third method, which is known as that applying the damping. So the third approach is to add the damping to the system. So damping doesn't always eliminate the resonance, it limit the amplitude buildup. Remember that changing the stiffness and the addition of mass will shift the natural frequency, but damping will not shift, but it will control the amplitude. Okay, so it's if for example you remember the anti-vibration mounts or isolators or damping material on the structure, what will happen, this will absorb some of the vibration energy and prevent the dangerous amplitude amplification. So in some cases a tuned mass damper is used, a secondary mass spring system tuned to the resonant frequency. What will happen, what these things do, this will effectively absorb the energy before it build up in the main structure. So you will be seeing in large industrial fans and the tall structures such kind of things. So in practice, the solution often combines all three methods, operating speed adjustment, structural modifications, or added the damping. Okay, so let me leave you with the three key takeaways from this video. The first one, that we have learned that every machine component has a natural frequency determined by its stiffness and mass. Second thing, important thing that we have learned in this video is this: when operating frequency matches the natural frequency, amplitude builds up dangerously, and that is known as the resonance. But remember, theoretically it builds up, but practically, since the machine is having the components, that's each and every component is having some kind of a flexibility, so that will absorb. So that's why the pile up is not that it's continuously add on, but it will be saturated maybe 4 times, 5 times, or 10 times, 20 times, like this. Okay, the third takeaway is this: engineer fix resonance by changing the operating speed, or you can say the modifying the structure, or adding the damping. So these are the three things that we have covered up. Now, since we have understand about we have covered up the resonance topic, so the next video in the series will covers the damping. So why it matters, how it measured, and how the engineer how it is the engineers, you can say, the main weapon, you can say, against the resonance. So make sure you are subscribed so you don't miss it, and if this video helped you, hit the like button, and it tells me that content is useful and help more engineers find it, right? So I will see you in the next one. Till then, take care and bye.